Hey guys, it's Newomaster, and welcome to part 2 of my binary to BCD and BCD to binary tutorial series. In this episode, I'm going to be explaining combinational binary to BCD converters using dabble, such as this one here. The advantages of using binary beats to BCD converters that use combinational logic as opposed to my serial converter or the sequential ones, which we built last time, is that instead of having to wait for all of your numbers to shift in, which takes a long time, you can have your number pass through the entire machine in parallel, which means you can do things like pipelining, and in general, since a lot of this logic is calculated in parallel, it tends to be a lot faster than our other methods. This one is for 8 bits, and it is only 12 ticks synchronized, counting our input and output repeaters, which is insanely fast, to be quite honest. I've showed this off in previous videos, but today we are going to be looking at how the logic in these actually work. How can you implement the double-dabble algorithm in this sort of fashion to create a unit such as this, and then we will be building one on camera. Not quite this compact or efficient, but it will give you the general idea of the logic so you can optimize it later. So without further ado, let's get into the actual logic of these devices. So before I get into explaining how we can implement the double-dabble algorithm into combinational Redstone logic, you first have to know, well, what the heck is the double-dabble algorithm? So if you don't know what the double-dabble algorithm is, I suggest you go watch that episode of the tutorial series. That's the first episode. Just stop watching this video right now and go watch that video. So, the way I'm going to explain this is I'm going to start with a 1-bit binary to BCD converter, combinational, and I will add more bits as we get more explained. So, blue blocks are going to represent my inputs, and red blocks are going to represent my outputs. Torches are going to represent something being on, and no torch is going to represent something being off. You'll see kind of how I do that later. And then these gold blocks are going to divide my BCD digits where I need them, kind of like over there. That won't come into play until later, but yeah. So let's start off with a 1-bit binary to BCD converter. This is probably the simplest thing you could ever make with Redstone. It's a line. If your input's on, your output's on. If your input's off, your output's off. Because, well, a 1 in binary is a 1 in BCD. And a 0 in binary is a 0 in BCD. And that's how I'm going to do it with the torches too. I'm just going to have a torch here represent on, and yeah, you get the idea. Alright, so 2 bits. We still can pretty much do the same thing. If we have a 1, we have a 1 in BCD. If we have a 2 in binary, we can just pass it straight through and have a 2 in BCD. If we have a 3 in binary, we can just pass it straight through and have a 3 in BCD. So these can just be lines. Now 3 bits. So we have the same idea. If we have a 4 in binary, we have a 4 in BCD. If we have a 7 in binary, we have a 7 in BCD. Nothing yet has required us to carry to a second tens digit in BCD, because nothing we have been able to input so far is greater than 9. Everything is less than 9. But as soon as we add a 4th bit, that is going to change. So let's add a 4th bit. Now we can enter things like 15, which is not, you can't represent 15 with a BCD digit. So this is not going to work anymore. We're going to need a tens digit, we're just going to need 1, since the highest number we can input right now is 15. So we'll just have this here for when we actually figure out what to do. Now, the double dabbles algorithm states that if a number in any digit is greater than 4, then add 3 before shifting. So if before we shift, we try to make a unit here. Let's say this orange stuff represents a unit that says if this number is greater than 4, then add 3. Well, the problem with these units is that they expect a number that is from 0 through 9. So this isn't going to work, because we can input something like 15 into this unit, and it won't know how to handle that, because, well, what is it going to do? Add 3 to it? If you add 3 to 15, you definitely don't get the desired output, even if we did have a carry, but we don't have a carry. So instead, what we're going to have to do is we're going to have our unit output here, kind of like this. Now this unit only gets numbers from 0 through 9. This unit right here. It doesn't care about this bit. It only cares about what it is receiving. And as far as it's concerned, the highest thing it can receive is a 7, which is perfectly fine. It will add a 3 to that before shifting. So 7, and you add 3. Here, let's make this 15. So we have a 15 here. We already know that this is just going to go straight through, so that's a 1. That's a given. The number is odd. And this is receiving what it thinks is a 7. So if I add 3 to this, I'm going to get a 10 output. And then when that is shifted over, we have our 1 in this digit right here, and a 4 in this digit right here. Since before a 10 was a 8 and a 2, and then when you shift it over, this digit gets a 4, and this digit gets a carry. So this technically would be 16 if you shifted it over, but in BCD, an extra bit, a fifth bit, is a next digit, so this would be 10. So now we have a fully working 4-bit binary to BCD converter. Let's do another example. Let's try something like 11. So, same deal. This number is odd, and this line is on, so it just goes straight through, and boom. And since this unit here is receiving a 5, which is greater than 4, it's going to add 3 to it. So it's going to output a 8, and when you shift that over, it becomes 16 in binary, or a 10 in BCD. And we have everything works just fine. So yeah, this unit works, and I'm gonna put a sign here so we remember what these orange things actually do, since it might be easy to forget. So this unit takes in numbers 0 through 9, and if it is greater than 4, it adds 3. Okay, so I'm not going to copy these signs every time we make these orange units, because spoiler alert, we're going to use more of these. But these signs should be plenty. So that's what the orange stuff means. Alright, so let's add a 5th binary bit. So let's get rid of these torches first of all. And 5th binary bit, go. Alright, so before we do anything else, first let's notice that, hey, this first BCD digit has 5 bits in it, which isn't right at all. So we're going to have to shift this gold marker here, which marked our BCD digit division before, over 1. So now this is our first BCD digit, bounded by kind of the first input, because the 1 is always a straight line. Like if you look at this converter over here, which is for 8 bits, you just notice that the 1 bit, which is, the binary is reversed, but still, the 1 bit is just a straight line. It will always be. Alright, so now what do we do? Let's say we want to input something like 10 in binary. Since now this is 1, this is 2, this is 4, this is 8. Well, now this unit is receiving what it thinks is a 2. So it's just going to output a 2. And this unit is receiving, well, there's no unit, so it just passes through. So we have an illegal digit, an illegal output. So if you remember correctly, last time when we did that, when we had an illegal output like that, and I'm going to move these back a bit so we can make room for our next unit, our next orange unit. So if you remember last time, what we did is when we had a situation like this where our output was too great for the BCD digit to handle, we added a new unit. And if you notice, this unit is shifted over 1. So if we add a unit right here, this unit will be receiving a 5. And when it adds 3 to that, we will get our 10 again in BCD, just like before. And this works because we might think, oh, well, this BCD digit has 4 inputs, so sometimes it might get this, right? No, it won't. It won't ever have a situation where this unit receives a number greater than 9. Because this unit before it, this one I'm standing on, will never output anything greater than 4 here. Like it won't output a 5, because when you input a 5 to it, it outputs an 8, because you're adding 3 to a 5. 3 is greater than 4. So it won't output anything on these 3 bits here greater than 4. So I can input a 4 here and get a 4 out right here. And then I can input a 1 here and get a 1 here. But that's 9. That's good. This is fine. So you're never going to get anything inputted into this second unit that's greater than 9. And that is due to the magic of our shifting double dabble algorithm. This is the implementation of the algorithm in action. Because this unit is receiving what it thinks is a 1 right here, and this next unit is receiving what it thinks is a 2 from the output of here. Just like that. And that is how the shift works in the converters, which is very important. That is how the shift is simulated without actually moving the bits physically shifting. Instead, you shift the units that do the conversion across the bits. So now we have a fully working 5-bit binary to BCD converter. Well, let's test it. Let's do our 31 operation, which we did last time down there, I think. I think the example's still down there. Let me check. Blah. Yeah, it is. So this unit is receiving what it thinks is a 7, and it's going to add 3 to that 7 and output what it thinks is a 10. And this unit is also receiving another 1 from here, and this line is just a 1, which gets passed all the way down there. Now this unit is receiving a what it thinks is a 5, because this was outputting a 10, which is an 8 and a 2, and when you shift over 1, you get a 4 right here, since this is now worth 4. And we have another 1 coming in from here. So this is going to output an 8, since 5 plus 3 is 8, and we're going to get our output of 31, 3, 1. Now, if we pay attention to what addition operations, we had the first operation, we added 3 to a 7, and we also added 3 to a 5. Now let's see if we look down here, that's the same thing that happens. Well, look at this. First shift, second shift, third shift, we have a 7. We add 3 to it. We shift again, and if we look here, we have the 5 right here that we also added 3 to. So the shift is perfectly simulated with this orientation of units in this sort of fashion. Now let's expand this to 6 bits, which should be fairly easy and should happen fairly quickly now that we know the pattern. So obviously we're just going to need, well, let's add the next actual bit. And we also need to place our BCD digit, since I actually kind of just completely destroyed the gold blocks. So the first 4 bits will be our first digit. So we will have a divider right there. Now when we input something like 5, or like 10 actually, 10 should be the, and these signs are now wrong since I added another digit, but we don't really need them. So this is 10 in binary. So now we have the same issue we had before. This unit is receiving what it thinks is a 1. Shift it over, this unit is receiving what it thinks is a 2. And then, well, this is 10, and this BCD digit can't handle that. So we do what we did before. We add another shifted over unit. And this unit will say, hey, if the number is greater than 5, add 3 to it. Or greater than 4, obviously. So this number is greater than 4, obviously. So we're going to add 3 to it, and we get 10 in binary, or in BCD. My words aren't working today, apparently. So now let's expand this to 7 bits, which will get kind of interesting, and you'll see why in a second. Here, let me expand these output lines just a bit. Alright, so we know we got to place our BCD digit marker, which is right here. And look here, we have a full BCD digit here. But we know that from our extensive knowledge in binary that, well, 7 bits can represent numbers up to 127. So before we even do anything, we're going to know, we know that we're going to need another BCD digit, our hundreds place, which will be right here. And I'll talk about that later. But again, I have to repeat this a lot since it's very important. If we enter something in like 10, it will go through these units, and this unit will receive what it thinks is a 1, and will output a 1. This unit will receive what it thinks is a 2, and will output a 2. And this one, so far, just goes straight through. And this BCD digit cannot handle the 10. So we do like we did before, and we add our shifted over unit, simulating the shift. And I'm going to bring this down 1 actually. Just like that. But now over here, we're going to have another problem. And that is, what if we have something like 100? And I do apologize, I don't have what 100 is memorized in binary. 1, 2, 4, 8, 16, 32, 64. So it'd be 64 96 100. Yep. So this unit is receiving what it thinks is a 6. Add 3 to that, we get a 9. Now this unit is receiving what it thinks is a 2, which was a 1 before. Remember the shift. This outputs a 1. Then this unit thinks it's a 2 since it's shifted. So this unit is receiving what it thinks is a 5 because we have this input down here as well. So it's going to output an 8. But uh-oh, look at this. This BCD digit is 10. And we can't have 10 in a BCD digit. So, hey, this kind of looks familiar. What should we do? We should add a unit here. A unit that says if this number is greater than 4, we add 3 to it, just like we did over there. And now our conversion works, and we have our answer of 100. If you were to add another bit, you're pretty much just continuing the pattern. I guess I can do it real quick. Oh, I forgot to move the, oh, but yeah. So let's move this bit. I was about to say that I forgot to move it for 7 bits, but I just added a bit. I'm so stupid. So we'll move this one over as well. And this is now for 8 bits. So we need to move this out a little bit. I'm gonna use roller bit this time. So again, let's continue the pattern. So we know that we're going to need another unit right here, like that. And then we know that we're also going to need another unit right here. Because hey, if this unit right here outputs an 8 and this unit here outputs a 2, then this is going to get a 10. So we need another unit to add 3 to the 5 and carry out to the next BCD digit. And there we go. There is our expansion for 8-bit binary to BCD combinational. And if we come over to this unit right here, it's going to be backwards because this unit is flipped for screens. But we can see the orientation of the units in that sort of fashion. We have these units here getting shifted, and then these 2 extra units like that. See the similarities? So that pretty much concludes the portion of the video on actually how the actual logic of the device works. In the next portion of this video, we're actually going to start building a combinational binary to BCD converter. So we are now ready to start building. The first thing we're going to need to do is we're going to have to figure out how we're going to make these units that add 3 when the number is greater than 4. Now, if you watched last episode in this tutorial series, then you know that the best way to do this is with a decoder that decodes for all of the possible inputs that the unit can receive, 1 through 9, and then uses a ROM underneath it to output the correct value of the number plus 3. So for 5, it would output an 8, like that. So, but we want to make our binary to BCD unit compact, so we're not going to use a flat decoder design like that. We are going to use a vertical decoder design like this, except it's going to be much more easy to understand because it's not going to be so condensed. I'm going to make it larger. So the first thing we're going to need to do is we're going to need to make our 9 decoder lines for the numbers 1 through 9 for our decoder. So our decoder needs to be this wide because we have 4 input lines. And then if we were to space this out, the next one right next to it, directly adjacent, it would look like this. So if we were to stack this, this is what the unit next to it would look like. Kind of like this unit next to that one. So now we just need to stack this up 8 times, so we have 9 lines. Just like that. Bam. Now we need to make input spirals for our inputs. So I'm going to make a spiral going in this direction, and then a spiral going in this direction. What this is going to allow us to do is this just carries the inputs up from the anywhere in the decoder. So instead of having come on, there we go. Instead of having these lines going across the top, we have spirals going up the side. Come on, there we go. So that should be our base spiral, and then I think if we select it here, and actually no, yeah, that'll work. Here and here, we can stack this up. Let's try it 3 times. That reaches moderately well. And then we can stack this to the side. Just once. Like so. And now you notice that these stacks neatly fit together. And signals should pretty much reach all the way up to the top. It's close. We can deal with this extra 2 blocks of signal length not working, and that will just kind of be special case wiring. So now, actually, I should demonstrate that this still stacks sideways too. So let's just select this. Due to the way that these power stacks are stacked, notice that there's no interference when I stack it like this too. So this would be 2 units next to each other. So now all we need to do is code for our decoder lines. So this first one is looking for a 1. So I'm going to put a torch here and repeaters on all of the other ones, because this is saying when this line is on and nothing else, then power the output. So something like this should work. And I think we can actually just do this. There we go. That shouldn't interfere with another line right here. So we're good. So when I power this, that line turns off. If I power this back on, that line turns back on. So now if we have a torch on here representing our output value, if we input a 1, we get out a 1. That's what we have so far. And I'm going to leave that for later. Now the next one, 2. Now we need a repeater here. So let's put a repeater right here. And now we need a torch here, because we're looking for this to be on now. And we also need a repeater here. And I think what I can do actually is have this power both of them like that, and maybe this one as well. No, I think I'll do them separately. Yeah, because there's a nice spot right there. And it was like this before. So now, let's say this is on. Neither the 1 nor the 2 should turn off when I turn this, because of that keeping it on. But if I turn this off now, you can see the 2 line is now activated, so I would have a torch here saying this is 2, pass the signal on, and if I get rid of this, that's back on, and if I turn power that, the bottom one is off. So yeah, basically, in terms of the binary value you're inputting, a torch means that the decoder is looking for it to be on, and a repeater means that the decoder is looking for it to be off. So let's continue this pattern. This next line is looking for 3, so we have a 1 here, and the second one also needs to be a 1. Now this is going to be kind of tricky. Let's see, what can we do about this? Oh, of course we can do this. Lol. Alright, anyways, moving on. Then we have repeaters here. What did I do? What did I do? I heard a torch burn out. Oh, ah! That was a mistake. And then we also need one last repeater from this line. Right, maybe here. Slab, maybe. Yeah, there we go. Alright, now on to 4. Oh, nope. It would have to be... Oh, I can get rid of that and then put it on this side so that when I stack it, it would be like this. Haha. Alright, next line will be a 4. So this needs to be off. And this needs to be off as well. And then this needs to be on. And this needs to be off. Now 5. This needs to be on. This needs to be off still, so I'm actually going to move this repeater up so it powers both of those lines at the same time. This also needs to be on. And then this last one needs to be off, like usual. And I'll move this one up as well, so it powers both of those. Beautiful. Now on to 6, which is 0, 1, 1, 0. So we know that this needs to be a 0. Consistency. That needs to be a block. Haha. Then a 2. That needs to be on, and a 4, which needs to be on. And then another 8, which needs to be off. And spoiler alert, the 7s also need to be off, so I'll just power both of those right now. Now for the 7, all of these need to be on, so that one needs to be on, power that one needs to be on, power it like that, and that one needs to be on, power it like that. And we have that repeater there already. Now for these last 2, finally we get to use this 8 line. So I'm actually going to do this. Like that, and then like that, since the 8 needs to power both of those anyways. And then we need a repeater for both of these for 4, since a 4 doesn't need to power any of those. And same with the 2. That means we can get rid of that. And then the 1 needs to power the 9. So let's see. There we go. See, this is what I meant when I said that we could work around it, the signal length, since I'm pretty sure this reaches now if we power it from like right here. Yeah, works fine. Alright, so now the only thing we have to do is stack this and put the torches in the correct spot so they power these spirals directly. So what I'm going to do is give myself some space. So let's see here. Put a world edit thing here and world edit thing here. So let's look at how we're going to stack this. We know that when we have one unit and then 2 units in front of it, we're going to have 1 unit kind of to the right slightly, and then 1 unit attached to the 8 output of this one. So we're going to have 2 units in front of this one. So if I copy this from here, let's say I want 2 blocks of empty space between them before my next one. So my next one will start right here. So when I'm copy pasting, this torch should be 2 blocks over right here. Oh, actually no. I need 2 more blocks of space since I forgot to account, 3 more since I forgot to account for these. So it should be right here. Voila! And then we have plenty of space in between here to connect them. And now we just paste another one next to it. Ooh, there's a problem. I guess we can just do it like this. I honestly do not think that this will change anything. Oh, and I also forgot, here, let's just do it on this. I forgot 2 things. I forgot that this needs to be stacked correctly, which can be fixed like that, and then I also forgot the repeater for this layer, for the 8, since you don't need a 1 to have an 8 in binary. So now let's just place this block here for a placeholder. Let's copy this again and paste it. There we go. Things should be working now. Perfect. And as you see down here, see how this is kind of staggered over? That works just fine. So now all we need to do is connect these. So what happened to this torch? That's odd. Ah! What am I doing? Okay, there we go. I must have broken this torch by mistake. So before we actually connect these, I want to test the decoder. So we have 1, nothing else is off. Then we have 2, nothing else is off. Then we have 3, nothing else is off. 4, nothing else is off. 5, 1, 2, 3, 4, 5, yes, nothing else is off, right? Yep. 6, 7, 8, and 9. So we're good there. This decoder works just fine. So now all we need to do is make this transmit the signal correctly. So we know that this one is going to be receiving our input from the next bit, or the bit before it technically. So the 1 output here is going to connect into the 2 here. So let's do this. Let's test that the signal reaches, and it does, which is brilliant. That's probably one of the harder ones to do. And then 2. We can do it right here. That powers the spiral next to it. And then 3 powers both of them at the same time. So we can do this, and then maybe we can move this one to right here. And bring a line down from here. So that should power both of those all the way up and all the way down, right? Yep. Now for 4, that will power this line. So 1, 2, 3, 4. So right here. This will work. Now 5, 5, 5, 5. For 5, you notice that this is powering into the next unit, like we should be. So 5 plus 3 is 8. So instead of just encoding for 5 as the output, we're going to have this output an 8, which goes into this next unit instead. And then same for the next one, which is 6 plus 3, which is 9. We'll have this output into this 8 spiral. And I think the best way to do that is like this. Actually, maybe like that. And then we also need a 1 down over here. Let's make sure that reaches. Oh yeah, that's fine. And then we have 7 plus 3, which is 10. And for this one, I'll do this. And then we need a 2 to power this. And now we have 8 plus 3, which is 11. So we have this 8 being powered like so. And then we have both 1 and 2 being powered over here. I think this will work. And then the last one will be 9 plus 3, which is 12. So we'll have 8 and 4. And I think I'll get the 4, since that torch needs to be directly powered. I think I'll bring the 4 line down a little bit. And this up. There we go. So now we should have a stackable unit that we can use to create our binary to BCD converter from. And that's one endpoint, and the other endpoint is down here. So if we select this with World Edit, we can now copy and paste it to make our binary to BCD converter. So let's do that. Let's make an 8-bit binary to BCD converter following this template we already have for us. So first of all, let's make some levers. Alright, so let's copy paste this unit the first time. And I think I want to input from like kind of the middle. So let's try like right here. So our first 3 inputs will be like that. That seems a little bit too low, maybe. Maybe like right here. Yeah, that looks good. So I will select this. And then I will copy it from this repeater. And then I will paste it right here, following our template. Hopefully that doesn't actually stick into the template. Nope, we're good. So everything should be fine. There should be no issues. Now the next one will receive input from here. So the next one will be sideways to the left 1. So I believe, let's see if this works. Maybe it's right here. I'll have to, yeah, there we go. And that is perfectly connected. And we are missing a power stack here. I'll have to build that manually later. So Now we just gotta find a way to bust this line beside here and power it into there. And I'm going to put this repeater on 2 ticks. Since this unit takes 2 ticks, it will be synchronized. And now all we need to do is continue this pattern downward. So from here, paste the next unit. And again. And we need 5 of these. So we have 3, 4, and 5. And obviously we will need to connect all these spirals up later. And I think I'll do that at the end. Now we need to copy this busing and paste that in. And we still need to insert 2 more. Oops. That's not what I meant to do. I meant to paste it. We still need to insert 2 more units next to these, of course, on the other side, right there and right there, as the template suggests. So if we paste our busing in, everything should be in working order. And we can stick another repeater here on 2 ticks for syncness. Alright, so now all we need to do is get those last 2 units in, so I'm probably going to need to recopy this. Blah. Blah. And let's see, where do we need to paste them? We need to paste them right to the left of the second to last one, and I'm right to the left of the last one. So I think I will copy it from right here. And paste it right here. Too close. Right? Is that too close? That is definitely too close. Hope that didn't mess anything up. Everything seems to be hooked up. Hooked up, hooked up. 1, 2, 3, 4, 5. Hooked up at 5. Hooked up. Hooked up. Beautiful. Now that just leaves, actually I liked that orange block, give me it back. That just leaves this last one. So we're going to have an output spiral here, and then output spirals here. So let me copy our output spirals, which also happen to be our input spirals. Alright. That way when I copy it here, it's in front of me. And then when I paste it here, it's also in front of me. And it lines up. Now I can just remove some of this extraneous stuff, like a lot of the stuff that you don't need. Yeah, most of the work that goes into making these things is very tedious stuff like this. It's very easy to accidentally break something. Like, I guarantee you that there is some problem with this somewhere that I messed up while I was building it. And to be quite honest, if I find an operation that doesn't work, I'm most likely not even gonna fix it, since it's unless it's like nothing works. But if it's like one operation that doesn't work, it's like, yeah, there's probably a missing torch somewhere, and I can just deal with it later. Any person who is actually building this to use would just debug it anyways. Alright, now I can just copy the edge spiral, which is this one right here. And after this, we just have a small amount more of busing, and then we can test it. And the busing that we have to do is, did I miss half of this spiral? I missed half of the spiral. I'm a pro world editor. No, not 12. Expand. I'll just reselect it. I do apologize for my derpy actions during this video. Plunk. That should fix our stupid mistake, right? Yeah. Fixed. And 2 more. There we go. Now all we gotta do is bust these together. So I am going to pick the middle ground that we used before, which happens to be right here. Put a 2-tick repeater on there and connect them up. And actually, in case there is any signal strength issues, I'm going to put 2 repeaters, one on the edge of each. And same thing for this one to that one. And these 2 lines are the same as that line and that line. And they are synchronized. Actually, no, that one is synchronized. This one is not. This needs 2 repeaters for that one, or 2 ticks for that one, and 2 ticks for that one, since this one is twice as far. And now we need this output right here. Again, I'll just use 2 ticks right there. And then we can make our output repeaters, which should be, if I did everything correctly, a nice stack of 9. Yep, boom. There we go. And we can just use our awesome gold output dividers and some lamps. So we have 1, 2, 3, 4 output division, 1's digit, 10's digit, and then output division on the last 2. All right. This should be in working order now. Let's try 128. And our output is 128. Bam! Double dabble. Woot. Let's do 255. Everything on. Bam, 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 bam. Hey. Bam, 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 bam. 255. 255. So, I think it is safe to conclude that we have made a working binary to BCD converter. Here, let's turn that off and see 127. 1, 2, 7. So, no bugs as far as I can tell so far. I mean, I probably could find one if I played around with it for long enough, but I don't feel like doing that. You guys can do that if you want. Find bugs in here and debug it. But anyways, that's pretty much it for this episode. We learned how to make combinational binary to BCD converters, and we built one on camera. The only difference between this one right here and the one down here is that there is far less space between the units, as you can see here. It does get very tricky if you decrease the space between the units. These units are only 5 blocks long. It gets really hard after a while, but it's worth it because it's really tiny and really awesome and really fast. Both of these are the same speed. But yep, that's it. Thank you very much for watching, and I will see you in part 3, where we do reverse double dabble and other BCD to binary converters. That thing and that thing. So yeah, see you next time.